Okay, folks, welcome to the last video of the semester. Video, I think it's 24, it might be 23, on chapter 5.3. And here we want to find the maximum or minimum of a function over a feasibility region. So we've, in 5.1 and 5.2, figured out how to draw feasibility regions. In 5.3, we want to find the maximum minimum of something, usually profit. And as we've pointed out in section 5.2, maximum or minimum will always occur at a corner point. So, problems 1 through 8 in the book, that would introduce the idea, so we'll do an example of that. And then problems 9 through 11, well, all these ones are just sort of mathematical problems. And then 31 through 43, these problems, those are all word problems. So what's the idea that's going on here? Well, here's a feasibility region corresponding to the following equations. 7x plus 10y is less than or equal to 70. This has got y-intercept 7 and x-intercept 10. So that's this line, 7x plus 10y equals 70. 10x plus 5y less than or equal to 50, so its x-intercept is 50 divided by 10, which is 5. Y-intercept is 50 divided by 5, which is 10. So that's this line, 10x plus 5y equal to 50. And this is the feasibility region that we have. So, and x greater than or equal to 0, y greater than or equal to 0. So that's in the first quadrant, less than this, so it's there. So, in these problems 1 through 8, they ask, say, plot a particular point. And actually in the book they give you the point. But let's plot the point 2, 3. So 2 is here, 2, 3 is about there. And for p, usually thought of as a profit function. So for p equals 3x plus 2y, plot the constant p line through these 2 points. So, p equals 3x plus 2y. If we're thinking about this point, if x equals 2, y equals 3, p equals 3 times 2 is 6, plus 2 times 3 is 6, is 12. Okay, so what are we thinking about this? This is some kind of a budget, right? Like, I don't know, in dealing with the furniture problems, right? Furniture had to be constructed and painted, right? So this might be your construction budget, this might be your painting budget, and you decide to make 2 units of one thing and 3 units of the other, and you get $3 or $2, could be $3,000 or $2,000, I don't know exactly what the units are, but $3 for each one of the x's you sell, $2 for each one of the y's. So if you choose to make 2 of the x's and 3 of the y's, you're getting $12. And what's the profit line that looks like this? If we're thinking of p of profit, well, profit there is 12, so it must be 12 equals 3x plus 2y. This would have, this line would have a x-intercept of 4, right, 12 divided by 3, and a y-intercept of 6. Right? So it would look like that. And this would be the profit equals 12 line. Okay, what about the point 3, 4? We can do the same thing. Suppose you said sell 3 x's and 4 y's. If you're selling 3 x's and 4 y's, p equals 3x plus 2y. If x equals 3, y equals 4, what's your profit? 3 times 3 is 9, plus 4 times 8, it's 17. Great. So the profit line through 3, 4, the point 3, 4 is, well, 17 equals 3x plus 2y. What does that look like? Well, that line has x-intercept of 17 over 3, which is just shy of 6, and a y-intercept of 17 divided by 2, which is 8.5. So 5 2/3 is your x-intercept, and 8.5 is your y-intercept. It goes to that point, So there is your profit equals 17 line. Right? These two lines are parallel. This profit line and this profit line, they're parallel because their slopes are both, if you solve this for y, going to be minus 3 over 2. Minus 3 over 2 would be a slope. So they're all parallel. Can you make more than $17? Well, this whole part of the feasibility region is feasible numbers of x and y's. You can make them because they're inside both budgets. That'll make you more than $17 because this side is the more than 17 side of this line, and this is the less than 17 side. Right? 12 is less than 17, and that's on this side. So where would P be maximized? Well, if you increase profit, you're going out this way, and you're always going out parallel to these lines. So where's the point that you would leave the feasibility region? Oh, right there, that point of intersection. Whatever that profit line, that's your max profit. And what's your minimum profit going to be? Well, as you would suspect, minimum profit would be when you make nothing. Right? So, what's the upshot of all this? Max and minimum of P equals 3x plus 2y occur at corner points of the feasibility region. Feasibility region. Right? It couldn't be this point, for example, because you could go down the boundary a little bit further and make more than $17, right? And it couldn't be this point because you can go up the boundary here and make more than $17. And as you keep this profit going up and to the right, eventually this will be the last point that will give you a feasible combinations of x and y's to make. And likewise, if you go back, right, this can't be your minimum because you can always make less by going down the boundary, and so this will be your minimum. Okay, so at one of the corner points, and if you draw the profit lines, you can figure out which corner point it is, often by looking at it. On the other hand, this is the same region as we had above, right? And we want the same points, 2 and 3 and 3 and 3, but now we'll look at a different profit function, 4x plus y. So for x equals 2, y equals 3, p equals 4 times 2 is 8, plus 3 equals 11. So we have our profit line through this point, x equals 2, y equals 3. That'll be here. What's the profit line with this profit function going to look like? It'll be 11 equals 4x plus y. Your x-intercept is 11 over 4, which is, well, 12 over 4 is 3, so it's a little bit under 3, 2 and 2/3. And your y-intercept is, well, y equals 11. And y equals 11 is way up here. 11/4, again, that's going to be 2 and 2/3. That's about here. And our profit line, this is the p equals 11 line, right? Because it's $4 for each x and 1 for each y, right? The ratio of x's profit they make on each x is 4 times the profit you get on each y. So the slope of this is going to be minus 4. It's very steep. As opposed to this, right? What's the slope here? 3x plus 2y. You get $3 for each x compared to 2 for each y, so it's 1.5. The ratio is 1.5. And so the slope here is actually going to be 1.5, well, minus 1.5. So this profit line is not as steep as the other profit line. Right? So what happens if we look at the point 3, 3? So did I want 3, 3 there, or did I want 3, 4? I actually wanted 3, 4, not 3, 3. for x equal to 3, y equal to 4. So 3, 4 would be up here, more or less, maybe a little below that, about there. Then your profit is 3 times 4 is 12, plus 4 equals 16. So what's the profit line through this point? It'll be profit equals 16, so 16 equals 4x plus y. X-intercept, 16 over 4, so it's 4. Y-intercept, y equals 16. Now y equals 16, that's way off the top of this. And this is the y-intercept. So 16 is way up here, 4 we know is there. So what's the profit equals 16 line going to look like? It'll go through 3, 4, up like that. Make 3, 4 over there. So this is the profit equals 16 line. I'm going to draw this out here so my lines don't overlap. There, profit equals 16 is this line. Great. So can you make more than $16? Sure, this entire region here is inside the feasibility region, so you can make more than $16 by moving out to the right this way. So where for this profit function is the maximum going to be? The maximum now is actually going to be there. That's the last place that these profit lines will touch the feasibility region as you increase the profit. So this is going to be your max profit line. There's no other place in the feasibility region where you can make more profit than down there. So you can't tell just by looking at the feasibility region where the maximum is going to be. This particular profit function on this feasibility region had a maximum here. This slightly different profit function has a maximum there. So find the maximum minimum, find all corner points, plug into P. The biggest number you get out is the maximum. Smallest is minimum. Okay, great. So let's look at a problem. Right? Doesn't have any. It's not a word problem or anything. It's just sort of a straight up problem. Here's a bunch of inequalities, and here's a function. Right? So these inequalities, graph these. Right? And then we want to find the maximum and minimum of this function over that region. Remember that these two mean only consider the first quadrant. We're only interested in x and y is greater than 0. So we really have 1, 2, 3 equations, lines that we have to graph and figure out which side they are. So we'll call this one 1, we'll call this one 2, and we'll call this last one 3. So for 1, what's the deal that we learned in 5.1 and 5.2 for dealing with this? X-intercept, to graph it, find the x-intercept and the y-intercept. X-intercept is 10, y-intercept is also 10, because we're dealing with x plus y equals 10. And use a test point. If you plug in 0, 0, it's less than or equal to 10. That's true. So 0, 0 is on the side that we want. 2, this equation, what's your x-intercept? X-intercept is 20. Right, set y equals 0, solve for x. Y-intercept is 20 divided by 4, which is 5. If you plug in 0, you get 0 plus 4 times 0, which equals 0, which is actually less than 20. 0, 0 is on the wrong side because we want greater than. So that one has to be, we want the side that 0, 0 is not on. 3, what's your x-intercept for that one? X-intercept here is 25 divided by 5. What's your y-intercept? 25. What's our test point? Again, 0, 0. 5 times 0 plus 0 is less than or equal to 25. So we want the side 0, 0 is on. Great, so now we can draw the feasibility region. Okay, we want only the first quadrant. There's my x-axis, there's my y-axis. This first line, x equals 10, y equals 10. So we'll put in a 10 and a 10. Line looks like that. And we want the side that 0, 0 is on, because 0 is less than 10. So that means we shade this side. And we write down here x plus y equals 10, so we know which line we're looking at. This line, we will do this one in red. So x-intercept is 20. That's out here somewhere. Y-intercept is 5. That's in here somewhere. And so our line looks like that. And this is the line. Second line is x plus 4y equals 20. That's our line in red. And which side do we want? We want the side that 0, 0 is not on. Right? So 0, 0 is over here. We want this side up here. So we shade this whole unbounded region in the first quadrant. We don't go over to the outside of this though. Great. What about the last one? Blue. Boink. So x-intercept is 5. Y-intercept is 25, which is up here somewhere. You don't really have to worry about, too much about accuracy. We're just sketching things. Great. So there it is. That's the third line, and we want the side that is 0, 0 is on. So 0, 0 is over here, so that means we want this side. Great. So which is the region that we sketched in all 3 times? We'll do it in green. This region. That's the region we're after. Great. Well, we're not done. We've sketched the region. What we need to do is find the maximum minimum of P. And what do we know about a maximum minimum of P? Find all the corner points of the region you're interested in, plug them into the function. The biggest number is the maximum, the smallest number is the minimum. So the next step, now that we've figured out what the region we're looking for is, we have to find the corner points. So let's go back to my black pen, and we will call these corner points A, B, C, and D. Very traditional. So this is corner point A, corner point B, corner point C, and corner point D. Great. So A is pretty easy to find. It's 0, 10. D is easy to find. It's 0, 5 because of the y-intercepts of this line and that line. But what is B? Well, that's the intersection of this blue line, which I forgot to write in what line it was. And that's 5x plus y. 5x plus y equals 25. So the blue line is 5x plus y equals 25. So what is B? Go back to my black pen. The point B is the intersection of 5x plus y equals 25 and this line here, which is x plus y equals 10. Right, and we want to solve for x and y, and as we learned in 5.2, right, the easiest way to do this would just be to subtract here to eliminate the y's. I don't even need to multiply anything. 5x minus x, that's 4x, y minus y, that's 0, 25 minus 10, that is 15. So x equals 15 over 4. Now I can plug that back into either one of these equations to figure out what y is. So I'll plug it into this equation. So 15 over 4 plus y equals 10. Y equals 10 minus 15 over 4, but 10 is 40 over 4. And so y equals 40 minus 15 is 25 over 4. Great. And so that gives us the point B. Likewise, the point C is the point of intersection of this red line, x plus 4y equals 20, and the blue line, 5x plus y equals 25. So I can multiply the top by 5. Let's see, we'll multiply this by 5, and so these two together will give me 5x plus 20y equals 100, and 5x plus y equals 25, right? And now I can eliminate the x because I've gotten the same coefficient on both of those. So if I just subtract here, what am I left with? 20y minus y is 19y. 100 minus 25 is 75. So y equals 75 over 19. If I plug that back into one of my two equations, say this one, we get 5x equals 25 minus 75 over 19. Right? That's what I get if I plug this in here and then move it over to the other side. 25 is 475 over 19 minus the 75 over 19, and so that gives us x equals to 400 over 19. Great. So now we figured out what the points B and C were. So let's move to a slightly tidier picture. So this is one computer generated. This is A, this is B, this is C, this is D. How do we find the maximum minimum of that? Well, we'll set up a table. What's my corner point? Well, how many corner points do I have? I've got 4, A, B, C, and D. What's their x and y coordinates? Well, the x and y coordinates for A, that's 0, 10. That's easy to read off the graph. For B, we did a little bit of work for. X is 15 over 4, y is 25 over 4. C, we also did a little bit of work for. X is 400 over 19, y is 75 over 19. And D, you can find the coordinates of that just off the graph. X is 0, y is 5. So those are the corner points. One of them has to be where the maximum is. One of them has to be where the minimum is. The easiest way to figure that out is just plug them into this formula. So at this point, what's P? 3 times 0 plus 8 times 10 equals 80. So that's what you get there. If you multiply this out, you get 3 times 15 is 45 over 4. Well, 3 times 15 over 4 plus 8 times 25 over 4. If you grind that through your calculator, it should come out as 245 over 4, which is about 61.25. If you plug the coordinates of C into P, you get 3 times 400 over 19 plus 8 times 75 over 19, which turns out to be 1800 over 19, which is about, as a decimal, 94.74. And then finally, if you plug in D, x equals 0, y equals 5, 3 times 0 plus 8 times 5, that's 40. Great. So all we did was figure out what the coordinates of the corner points were, plug them in coordinates in here, and see what P was. And this is the biggest one. That's our maximum. So the maximum occurs at vertex C. Where's our minimum? That's there. That's our minimum. And that occurs at D. So max D there is the minimum. Great. So our profit lines are probably sort of very steep lines that look like this, and so they leave here, they enter there, and they leave there. And in particular, they have to be steeper than this line. So that gives us our maximums and minimums. Pretty straightforward. Once you have the corner points, you just plug them into the function that you're interested in. Okay, and then we have word problems. Bob has a factory that makes tables and chairs. This is a problem that we set up in 5.2. Each table takes 4 hours to assemble and 1 hour to paint. Each chair takes an hour to assemble, an hour to paint. He has 200 labor hours available each day for assembly and 100 labor hours available each day for painting. $30 on each table for profit, $5 on each chair. How many tables and chairs should you make to maximize his profit? So if we go back to 5.2's video, we actually set this up. Right? How do you solve a word problem? You set up a table. So we need to know how many tables and how many chairs should he make. So 4 columns will turn out. Table, chairs, and totals. And we'll give them variables, x and y. And what else do we need to know? Assembly. How long does it take to assemble things? Well, if you're making x tables and each table takes 4 hours, that's 4x. Painting. How long does it take to paint things? Well, each table takes an hour to paint. So if you have x tables, it'll take you x hours. For chairs, chairs takes an hour to assemble, so y chairs, that means y hours. And each chair takes an hour to paint, so you have y hours devoted to painting. Let's put in some columns and rows there. Totals, there's no totals for the variables. But we know assembly, you can't go over 200, and that's how many hours you have. So however many hours you take for assembly of tables and chairs, it's got to be less than or equal to 200. You have 100 labor hours available each day for painting, so it's got to be less than or equal to 100. And now, unlike 5.2 or 5.1, we have another thing to consider. Profit. We'll put in the line there. $30. So if you sell X tables, you get 30X. And if you sell Y chairs, you get 5Y for that. So your profit then is 30X plus 5Y. And the goal here is to maximize this. Make that as big as possible. Okay. So in 5.2, we set up the feasibility region. Right. This was the table axis, X. This is my chair axis. So number of chairs I make, Y. This was the assembly budget. And this was the painting budget. The assembly budget, 200 divided by 4. Oh, no, 200 divided by 1. The Y intercept will be 200. 200 divided by 4, that'll give you the X-intercept. And 200 divided by 4 is 50. The Y X-intercept for painting, that's 100. And the Y-intercept for painting is also 100. And so this was our feasibility region. And so that gives us 4 corner points. And we'll call these A, B, C, and D. And in 5.2, we found the coordinates of this to be 100 over 3 and 200 over 3. So, great. Once we're at this point, we know all the corner points. How do we maximize something? Well, we have to set up our table. Corner points, A, B, C, D. And then what are the coordinates? A is a y-intercept, so it's 0, 100. B, we figured out in the video for 5.2, so 100 over 3, 200 over 3. C, that's an x-intercept, so it's at 50, 0. And D is the last corner point, that's the origin. And then we want to maximize P equal to, what's my profit function? Slide up a little bit, come on. There we go. Profit function, 30x plus 5y. We want to maximize that. So we just take our x's and y's and plug them into this function and see what I get. So at A, he's selling 100 shares. 100 shares and no tables, right, at this point. So it's 100 shares and no tables. So he's making no profit off of tables, 30 times 0, plus $5 for each chair. So 5 times 100. He makes $500 at point A. At point B, he's making 100 over 3 tables, so 33 1/3. You know, and the units might be thousands of tables or something. So 30 times 100 over 3 plus 200 thirds chairs at $5 a chair. We get that, and if you actually multiply everything out, it's 4,000 over 3, which is 1333.33. 1333. $1,333.33. So that's how much profit he's making at B. How about at C? At C, he's making nothing but tables, and he's making 50 of them, and no chairs. 30 times 50, that's 1,500. And at D, he makes no tables and no chairs. Unsurprisingly, if you don't sell anything, your profit is 0. So that's a minimum profit. This, then, is the max profit. Making nothing but tables. That's what maximizes his profit. So all of chapter 5 then is pretty much in this problem, right? Given this kind of a word problem, set up a table that expresses what it is you need to find, your variables, your various budgets, the thing you're trying to maximize and minimize. Use the inequalities to draw the feasibility region. Always remember, especially in word problems, we're only looking in the first quadrant. Once you find the feasibility region, find the 4 corner points or 5 corner points, however many corner points there might be, and then you can set up a little table. Here's my corner points, coordinates of my corner points. This is the thing I'm trying to maximize and minimize. Plug each corner point